Hi, this is a section 3.5 example. I'm Amanda Olson, and this is Math 2410 at MCC. So for this problem, for this section, really, we are talking about, I should say, if you are in my hybrid class, this is example 18, 19, and possibly 20. We'll see how far we get from the practice problem reviews. So this problem asks us to find the limit if it exists, and they give us a function. And we're looking at x approaching infinity. On a graph, when you're looking at x approaching infinity, you're really talking about, as x increases without bounds or as x decreases without bounds, is your function approaching something? So if your function is approaching a value, that's going to be equivalent to a horizontal asymptote because you're looking at y approaching something for your graph. So if you've taken a college algebra class, you may have been presented with some theorems and some ways of saying, hey, if you have a rational function and case 1, case 2, case 3, the degree of the numerator is greater than the degree of the denominator. And there were some theorems like that. These theorems can also be found in your textbook, but they're really kind of algebra-based theorems, but they do give insight to a way, if you're looking at a problem, to say, okay, what's going to be my horizontal asymptote, which is really discussing the limits as x approaches infinity or negative infinity. For this one, I always like to try direct substitution first. If I were to try those guidelines, I don't have a single rational function. So one of the things I could do is I could say, okay, well, we need to get, a common denominator. So I'm going to have x as my common denominator so that I can add these two functions together. And when I do that, I get x plus 1 over x. And then I see that my degree of my numerator is equivalent to my degree in my denominator, which tells me based on those algebra rules that my horizontal asymptote is going to be the ratio of the degree in the numerator, which in this case is 1, over the ratio of the degree in the denominator, or the leading coefficient in the denominator. So that tells me that I'm going to have the line y equals 1 as my horizontal asymptote. But there's also a way to do this using limits. So for this, we changed our original problem of 1 plus 1 over x into the limit as x approaches infinity for x plus 1 over x, which based on our rules of algebra, we know this is going to equal 1. That function is going to approach 1. But we also, like I said, could have done this using just strict limits. So one of the things I like to do if I'm going to evaluate this is I like to see if direct substitution is possible. And in a way it is. The limit as x approaches really anything of 1, that constant, is just going to be 1. And then from there, if we think about direct substitution, we could say the limit as x goes to infinity, we end up with like a 1 over infinity. That's going to go towards 0. There's a theorem in this specific section that says the limit as x goes to infinity of 1 over x is equal to 0. So here we end up with 1 plus 0, which gives us 1, which tells me that the value of this limit is 1. So there's sort of two different ways of thinking about it. We can do that then to look at other similar ones. Again, this is really equivalent to a horizontal asymptote problem. So my function that I'm talking about in this example, which I should note, this example comes from number 19 on the practice problem review for my hybrid class. It is also, though, an example from section 3.5, but it involves f of x, and we have f of x equals x squared. I'm going to switch those first two terms, so it becomes negative 2x squared plus 1. Well, my degree in my numerator and my degree in my denominator are both the same. They're both degree 2. So my rules of algebra say, okay, well, the horizontal asymptote is going to be the leading coefficient in the numerator over the leading coefficient in the denominator. So it says that I'm going to have a horizontal asymptote of y equals -1/2. This means that as x approaches infinity, this function is going to approach -1/2. So that tells me that the limit as x approaches infinity, my function is going to -1/2. So that's enough to conclude that the value of this limit is equal to -1/2. But again, if you don't want to use those rules of algebra that you learned, you can use some calculus properties of limits to evaluate this. So what I like to do is I like to find a function that agrees at all but one point. That's equivalent to this entire function, all but one point. Specifically, this is going to be a function that agrees at all but the point except when x is equal to 0. So then we have a limit as x approaches infinity. This becomes 1 over, when I distribute this, this becomes a -2 plus 1 over x squared. Now, my starting function and my new function, they agree at all values of x except when x is equal to 0. And there's a theorem that says that their limits then are going to be equivalent. And this new function, I can now find the value of it's going to be 1 over -2 plus the limit as x goes to infinity of 1 over x squared. Since 2 is a positive rational number, we can then conclude that the limit as x goes to infinity of 1 over x squared is going to be 0. So this is going to equal 1 over -2 plus 0 or -1/2, which again fits what we saw earlier. Okay, and then let's just do one more. So a similar idea. Looking at this, what happens as x approaches -infinity? Do I have a horizontal asymptote? Let's consider. As horizontal asymptotes tell us what y or f of x is approaching as x approaches positive or negative infinity. So my rules of algebra say, do I have a horizontal asymptote? My degree in my numerator is greater than my degree of my denominator. My degree in my numerator is 2. My degree in my denominator is 1. So that would tell me that there is no horizontal asymptote. So we can say no HA exists, which probably tells me that this limit is not going to exist. But let's just consider it again algebraically. So the limit as x approaches -infinity of 2x squared over x plus 6. I multiply numerator and denominator by a well-chosen 1. In this case, I'm going to do 1 over x squared. Actually, let's do 1 over x. So then this is going to equal, it's going to have the same limit as x approaches infinity. We get 2x over 1 plus 6 over x. This is going to equal the limit as x goes towards -infinity of 2x over 1 plus the limit as x goes to -infinity of 6 over x. The denominator is going towards 0. And so I'm going to end up with a -2 times infinity or negative infinity. So you can put, hey, the limit does not exist, or if you want to include negative infinities, our textbook counts those as limits, even though sometimes limits should be defined as like specific values, not just infinity, because that's not a specific value. So some textbooks, some mathematicians argue the limit does not exist. Others say, it approaches negative infinity. That's what the limit's asking, really. So we put negative infinity. You could put either one for this and it will be counted as correct. All right. Thank you.